today we'll be seeing the fifth unit, that is the secondary storage. So in this unit we'll be seeing more about the secondary storage, as most of the things nowadays whenever memory comes to the picture, ultimately what is stored is in the mass storage device or the secondary storage. So here we'll be seeing the overview of the mass storage structure, then how is the disk structure, how it is organized, then the disk attachment, then the various disk scheduling algorithms, how exactly the sectors are assigned and accessed, the disk management, and finally the swap space management. So firstly, with the overview of the mass storage structure, so there are magnetic disks generally provide bulk of the secondary storage in modern day computers. Transfer rate is generally very high, and is the rate at which data flows between the disk and between the drive and the computer. Drive generally rotates at 60 to 250 times per second. Now, a very important term which is used in case of mass storage is the seek time. So it is the time to move the disk arm to the desired cylinder. So it determines how fast a particular data will be accessed when it is stored in the mass storage device. Disks are generally nowadays removable, and the drive is attached to a computer via I/O bus. The buses now vary. They can vary because they consist of various types. The buses can be USB, they can be SATA, ATA, that is ATA and SATA, the fiber channel, SCSI, that is the SCSI, as well as firewire. This is the moving head disk mechanism. Now the magnetic disks are generally organized in the form of platters, which you see over here. So they are organized in the form of platters. So there are various platters present to store the data, and the platters are again divided into tracks. So you can see concentric circles over here, which indicate that there is a tracks which are comprised in case of platters, and the tracks again are further divided into various different sectors. So each small space between the tracks is called a sector. So there is a read-write head which is assigned to each of the platter, and through that the reading and writing of the disks is generally taking place. So also there is a spindle which continuously rotates, and due to which the read-write head is positioned at various sectors, due to which the data can be accessed from the disk. Next we come to the disk structure. Disk drives are addressed as a large one-dimensional arrays of logical blocks, and here each logical block is the smallest unit of transfer. Generally, these logical blocks are formed by low-level formatting on the physical media. Now, sector 0 here is the first sector of the first track on the outermost cylinder. Mapping proceeds in order through that track, then the rest of the tracks in that particular cylinder, and then through the rest of the cylinders from outermost to the innermost. Logical to physical address translation is generally very easy, but this can get complicated because the sectors might get damaged. So there can be bad sectors existing, due to which the mapping might vary. Next we come to the disk scheduling. Now the operating system is responsible for using the hardware efficiently. Now in case of disk drives, this means that the operating system is responsible for providing fast access time and providing good disk bandwidth. Now the intention always for the operating system is to minimize the seek time. So if the seek time is minimized, that means the seek distance is minimized, which in turn means that the access will be generally faster. Then the disk bandwidth is given by the total number of bytes transferred divided by the total time between the first request for service and the completion of the last transfer. Now there are various sources of disk I/O requests. These can be from the OS itself, the system processes, as well as from user processes. Now the OS will generally maintain queue of requests per disk or particular device or for a particular device. Now whenever a IO is taking place, OS will search for a particular data on the particular disk. So that is why OS will generally have IO requests sometimes. IO request also includes input and output mode, disk addresses, memory addresses, and a number of sectors also to transfer. Now these can be generated either by system processes or whenever user asks for a particular data which is stored in a particular disk. Now there are the idle disk can exist which can immediately work on an IO request as it is free. Whenever an IO request comes into picture, the idle disk will immediately access or grant access to the data. So the data access will be faster. Whereas whenever a busy disk comes into picture, the data access will be slower. Now whenever the busy disk is present, disk is busy, at that time what happens is it will be performing some IO operation, that is the disk IO, and due to that it is busy in performing that particular disk IO whenever a request comes in. So that is why whenever a new request comes in, it cannot be accessed or granted access immediately. That is why the access to the data might be slower when compared to the idle disk. So that is why there are certain optimization algorithms are necessary, and they make use of a queue, and depending on how the queue is addressed, it decides how fast access will be. Next, we come to the disk scheduling. So here the drive controllers generally have small buffers and they can manage a queue of IO requests and which can be of varying depth. Several algorithms exist to schedule the service of disk IO requests, and this analysis is generally true for one or many platters. Now we will see the various scheduling algorithms. Here we are assuming that the request queue is ranging from 0 to 199, and the queue actually which is present is the cylinders at particular locations which are mentioned here, that is 98, 183, 37, 122, 14, 124, 65 and 67, and the head is pointing at the 53rd cylinder. So the first algorithm which we'll see is the FCFS. So as the FCFS name, it stands for first come first serve. So it's the simplest disk scheduling algorithm. So whenever the queue is present, the head will be moved simply to the first request within the queue. So that is what first come first serve means. Whichever request comes first, that will be addressed first. So here the head is actually starting at the point or is pointing at 53rd cylinder. So next, if we check the queue, it is pointing. The first request is at 98. So the head movement will be from 53 to 98. Next movement is from 183. So next movement will be from 98 to 183. Then the next request is 37. So the head will move to the 37th cylinder. Then it will move to the 122nd cylinder. Then to 14. Then to 124. Then to 65, and lastly at 67. Now here we need to calculate what is the total head movement. So the head movement is generally calculated by subtracting the final position of the head with respect to its earlier position of the head. So whenever the head moves from 53 to 98, the head position is calculated as 98 minus 53. The next head position will be, whenever it moves, will be from 98 to 183. So the difference is 183 minus 98. Next, the head moves from 183 to 37. So 183 minus 37. Then the head will move from 37 to 122. So 122 minus 37 will be the difference. That is by the amount by which the head moves in terms of number of cylinders. Then the head moves from 122 to 14. So the difference is given by 122 minus 14, as you can see here. Then it will move to 124. So the difference is 124 minus 14. That is the difference in head moment. Then the head moves from 124 to 65. So 124 minus 65 will give you the head moment. And finally, the head moves from 65 to 67. So 67 minus 65 will give you the head moment in terms of cylinders when the cylinder moves from 65th cylinder to 67th cylinder. So if you add this all head moment together, what you get is the total head moment, and it will come out to be 640 cylinders. So this illustration shows how the movement will be, and whenever generally it is asked, the question might be that you might be asked to explain the FCFS disk scheduling algorithm and also calculate the total head moment in terms of cylinders given a particular queue. So this will be an example of how you should be able to calculate the movement and in terms of number of cylinders. So this comes out to be, as you can see, 640 cylinders. So the next algorithm which we will see is the shortest seek time first, or SSTF in short. The shortest seek time first selects the request with the minimum seek time from the current head position. So it's a variation of from FCFS, and what you can see is SSTF you can treat it as a form of SJF, that is the shortage of first scheduling. So it selects the request which causes the head movement by the smallest amount. Hence the name is shortest seek time first. So as you can see, the queue here remains the same and head position starts at 53 again. So now among what happens in SSTF is, here in case of this SSTF, the OS will search for the request which is closest from the earlier head position. So the head starts at 53. So among the queue which is existing, the nearest location to which the head can move is 65. So the movement is from 53 to 65, then 65 to 67, then 67 to 37, then 37 to 14, then from 14 to 98, then 98 to 122, then 122 to 124, and lastly from 124 to 183. So this movement again needs to be calculated, and again it has to be determined what is the head movement in terms of cylinders. So firstly, as we have seen for FCFS, we'll do the same procedure for calculating the head movement in terms of cylinders for SSTF algorithm. So the head starts generally is starting at 53. So the head movement for the first case is it will move from 53 to 65. So the head movement is 65 minus 53 in the first case. Next it will move from 65 to 67. So the head movement is 67 minus 65. Then it will move to 37. So this head moment is captured by calculating 67 minus 65. Then from 67 minus 37, sorry. Then it will move from 37 to 14. So this moment is calculated by subtracting 14 from 37. That is 37 minus 14. Then from 14, the head moment will be to 98. So the calculation will be 98 minus 14. Next, it will move to 122. So the calculation of head moment is 122 minus 98. Then the head will move to 124. So the calculation is 124 minus 122. And lastly, it will move from 124 to 183. So the head moment here in this scenario will be 183 minus 124. So if you add all the head moment together, what you will get is the total head moment for this queue whenever it is using a SSTF algorithm, and in this scenario it comes out to be 236 cylinders. So total head movement in this scenario comes out to be 236 cylinders. Now this is about the shortest seek time first, or SSTF algorithm. Now there is another algorithm, or this scheduling algorithm, which works in a different way, which is the scan algorithm. So in case of the scan algorithm, the disk arm starts at one end of the disk and moves towards the other end, servicing requests until it gets to the other end of the disk. Once it reaches to the other end of the disk, the head movement will be reversed and the servicing continues in the opposite direction. Hence, the scan algorithm is also sometimes called as elevator algorithm. It's like the elevator starting at the ground floor and moving towards the top floor, stopping at each floor. Once it reaches at the top, then its direction is reversed and it goes on coming back to the ground floor, again servicing or stopping at each floor. So here you'll see what will be the total head movement. It will be mostly 208 cylinders. We will calculate it actually. So if we see here now, the queue is remaining the same and the head is starting at again at 53. So now as per the scan algorithm, the disk arm, that is the head, will move in only one direction. Once it reaches the other end of the disk, it will move in the opposite direction, servicing requests along the way. So the head is starting at 53, so it will move to the next location in one direction, that is to 37 among the queue. Then it will move to 14, then it will move to 0, and once it reaches this end of the disk, it will move in the opposite direction, and again servicing requests which come along the way when it is moving in the opposite direction. So it will move from 0 to 65, then it will move to 67, then it will move to 98, then 122, then 124, and finally stop at 183. So again we can need to calculate the total head moment in terms of cylinders. So since it is moving in this direction, the start, the first movement will be from 53 to 37. So 53 minus 37 will give the head moment in that scenario. Then it will move to 14. So 37 minus 14. Then it will move from 14 to 0. Now, and then it will move to 65. Now here there is no need of actually considering 0. This is a meaningless to move the arm from 14 to 0 when it could have directly gone from 14 directly to 65. So you need not consider 0 while calculating the head movement, because scan algorithm works in this way that it works and moves towards the one end of the disk, so it moves towards 0. So as this is not present in the queue, you need not consider this while calculating the total head moment. So the head moment is, when calculating, you need to calculate from 14 directly to 65. So that is why the head moment here in this scenario will be 65 minus 14. Then it will move to 67, so 67 minus 65. Then it will move to 98, so 98 minus 67. Then it will move to 122, so 122 minus 98. Then it will move to 124, so 122 minus, sorry, 124 minus 122, and lastly it will stop at 183, so 183 minus 124. So if you add this all together, you will get a total head moment of 208 cylinders. So which is what was present over here, that the total head moment predicted was it will be 208 cylinders. So in this we have calculated actually and seen that the head moment is actually 208 cylinders. So here what is happening in case of scan algorithm is it is unnecessarily moving and going to a particular cylinder which is not at all accessed and not required as per mentioned in the queue. So this is one of the disadvantage. So as a change over this, there is a C-scan algorithm or circular scan. So this provides a much more uniform wait time, and the head moves from one end of the disk to the other end of the disk, servicing requests as it goes. But the difference between scan and the circular scan or C-scan is that when it reaches to the other end, it immediately returns to the beginning of the disk without servicing any requests on the return trip. So this is a very important change from the scan algorithm. When the head reaches the other end of the disk, it returns to the beginning of the disk without servicing any requests on the return trip. So this treats the cylinder as a circular disk that wraps around the last cylinder to the first one. So here again we need to calculate the total number of cylinders. So we will see how it, in case of this algorithm, how the head will return back to the other end without servicing any request on the return trip. So the queue is maintained the same, and the head is starting again at 53. So here you can see the servicing is taking place in one direction, but as soon as it reaches the other end of the queue, although there are intermediate requests present here, what is happening in circular scan is it will move, once it reaches the one end of the disk, it will move to the other end back, but without servicing any requests along the way. Whereas if this was a scan algorithm, here you can see there is 37 and 14 remaining. It would have, after coming, while coming back in the opposite direction, it would have serviced 37 as well as 14. But circular scan treats the cylinders as a circular disc that wraps around the last cylinder to the first one. Due to that, whenever it reaches one end of the cylinder, it will move back in the opposite direction to the end without servicing any requests which are present along the way. Now here we need to calculate what is the total number of cylinder movement, that is the head, by what amount the head moves in case of, in terms of number of cylinders. So it will firstly the head movement will start at 53. So the calculation will be or the movement will be 65 minus 53. Next it will move to 67. So it will be 67 minus 65. Then it will move to 98. Then that will be 98 minus 67. Then it will move from 98 to 122. So this movement is captured by subtracting 98 from 122. So 122 minus 98. Then it will move to 124. So 124 minus 122. Then it will move to 183. So 183 minus 24. And now here what happens here is, since it moves to the 199, that is the last location in the queue, you have to consider this 199 while calculating total number of cylinders by which the head moves. So that is why you have to calculate one or include this in the calculation for the head movement. So this is 199 minus 183 and 199 minus 14. So again, when the 0 comes into picture, it's again meaningless, so it may not be considered. So the actual head moment here, what is happening is from 199 to 14. So that is why it is calculated as 199 minus 14. And then again from 14 to 37. So this is 37 minus 14. So if you add this all together, the total number of movements or total number of head movement in terms of cylinders is 354 cylinders. Now to overcome this disadvantage of moving towards the one end to the other end when it is not required, which is the disadvantage, there is another algorithm which overcomes this advantage, which is called a look algorithm. So loop is a version of scan, and similarly you have a circular loop or C loop, which is a version of C scan. So in this scenario, arm will go as far as only the last request in each direction, and then it reverses the direction immediately without going first all the way to the end of the disk. So now if you see in the scan algorithm and C scan algorithm, the arm is moving to the one end of the disk to the other end of the disk, which is unnecessary and not required because it will increase the seek time. So as a improvement over this, in case of look algorithm, the arm will go only to the last request, and whenever it reverses the direction, it will go again in the opposite direction, but not to the end of the disk. So it minimizes the seek time compared to scan and C scan. Now, similar to look, scan and C scan, we need to calculate the number of head movement in terms of C look and look. So if you consider C look algorithm, the queue and the head start remains the same. So you can see here the movement is from 53 to 65. So 65 minus 53 will give you the movement. Then 65 to 67. So 67 minus 65. Then 98 minus 67. Then 122 minus 98. Then 124 minus 122. Then 183 minus 124. Now here, in case of if you had considered C scan, the movement would have been from 183 to 199, which was not required as it is not present in the queue. So this will only go up in case of look algorithm or C look. It will go only up till the last request. So that is why the last request is 183. So this movement won't be from 183 to 199. Directly from 183, it will move back to 14. So the subtraction will be from 183 minus 14, then 37 minus 14. So the total number of head movement in terms of cylinders here in case of C look will be 322 cylinders. So if you compare this with the C scan, which is the alternative version of C look, you can see the number of head movement has decreased in terms of cylinders. So in case of C scan, the total number of head movement was 354, whereas in C look, the total number of head movements in terms of cylinders is only 322. So the seek time has been reduced when you consider the C look algorithm. Next, we consider how a disk scheduling algorithm has to be selected. So the SSTF or shortest seek time first is common and has a natural appeal. Because it provides the shortest seek time, so it reduces the seek time. So that is why SSTF is the most common one. Then scan and C scan also perform better for systems that perform or place a heavy load on the disk. So in those scenarios where the disk have a heavy load, scan and C scan are generally preferred. Then performance depends on the number and types of requests which are coming in. The disk scheduling algorithm but has to be written as a separate module by of the operating system, and this allows it to be replaced with a different algorithm in case it is necessary. Either SSTF or look is a reasonable choice for the default algorithm. Now we come to the disk management. So low-level formatting or physical formatting divides a disk into sectors, and the disk controller can read and write. Now each sector can hold a header information which includes data plus the error correction code, that is ECC. Logical formatting will generally create a file system. To increase the efficiency, most file systems group blocks into clusters. So whenever disk I/O is done, it is generally done in terms of blocks, whereas file I/O, whenever it is done in terms of clusters and not blocks. Raw disk access now for apps is provided that want to do their own block management. So this keeps the OS out of the way. So that is why the seek time is again reduced. Example or a standard example of this scenario are databases. Now boot block generally initializes the system. So the bootstrap loader or the bootstrap program is stored in the boot blocks of the boot partition. So this is how generally disk management takes into or is done in case of operating system or a computer system. So what we have seen today is what is the overview. We have seen today what is the mass storage structure, then the disk structure, the disk attachment, disk scheduling algorithms, as well as how to select a particular disk scheduling algorithm, and lastly we have seen the disk management. So in case of any doubts, you can ask me, and we'll continue with the remaining unit in the next lecture.